So, our next speaker, actually, he just started working for me 25 days ago, and we told him on Tuesday he had to give a talk. So we're hazing the new guy, right? But he has a very experienced career. He was the barista champion 2 years in a row. So if you ever need a cortada, he's the guy who's going to do it for you. Everyone, please welcome Gus.
Hey, everyone. Ooh, let's go back a slide. So, like Jared said, I actually volunteered. They only mildly hazed me, but I'm very excited to be here and talk about machine learning for people. And so normally I hate agenda slides, but since I'm going to be all over the place today, I thought I'd give you guys a little softball. So we've got some motivations. I'm going to set the stage for a story, and then we're going to talk through that story and preview some data, make some models, compare results and efficacy, and then think beyond those models and this particular story and think how we could apply these lessons to future ones. And then sum everything up for a nice little moral story. And so jumping in with our motivations, I want to know, how can I create a model that is easy to use and understand? And so in a world where we've got like ChatGPT and all that, you don't actually really know what's going on or how it works. And so if, let's say you're building a model for a less technical team, they really want to know what's actually happening in your model. If you just give them a number and you go, hey, my model says go do this, they're like, no thanks, that computer's not my boss. And if maybe you just care about the measured impact of the independent variables and not actually as much about the end result of the model. You're just trying to figure out what's actually going on here and why is this happening. And then a lot of the times these are business questions rather than technology questions. And so if I set the stage, this is my old car. It's a 2008 RAV4, a base model, 4-cylinder. And I always want to know when I'm driving, how many miles do I have remaining? How far can I actually go? And so here's my instrument cluster. And we've got my fuel gauge, my gas light, and my trip odometer. And so this particular trip, you'll notice I'm 327 miles in, I'm on empty, my gas light is on, and my tires are low on pressure. I was very worried about running out of gas. And a little bit of extra info for you is this particular car gets 20 city, 25 highway, and about 22 combined rated from the EPA. And so I made myself a Google form to collect my own data. And every time I went and got gas, I always filled up. I always filled out my Google form or took a picture of my instrument cluster and then filled out the form later. And so over about 2.5 years with the car, I always knew I had my distance traveled, I knew how many gallons I had put in the car, I had my price per gallon, I wanted to know if my light was on, and then I measured the gauge level in the highest fidelity I could because it's continuous, and I rounded it to the nearest about quarter. So I said, there are 4 tick marks, it's out of 4, and it actually went from negative 0.25, because if I really wanted to run it, I could go below empty. And so I ended up with 173 rows of data. And this is just a quick little bit that it looked like. So again, gallons, price per gallon, light, gauge level, and distance, and then a timestamp. I never really did anything with the timestamp besides look at how much I was spending on gas every month. And I computed some more columns. I had my total cost, gallons remaining, so I know, or Toyota told me that my tank was 15.9 gallons, and so I subtracted how many gallons I put in, and that's how much gas I had remaining. I have my miles per gallon, how much I spent per mile, the actual amount of gas, like what the gauge should have said, percent error between what the gauge said and what it should have said, and an estimated miles remaining. And so if I start thinking about machine learning and how I can apply it, I've got some goals to keep in mind. I don't want to run out of gas. And because I'm driving, I want to be able to compute my miles remaining while I'm sitting in the car. And that's sort of tricky because I can't pull out my phone. That's illegal, and I would never break the law. And not just do I want to know how many miles remaining, like at one moment if I pulled over, let's say, I want to know at any time. Because maybe I'm coming up to a rest stop and there's a gas station, it says next rest stop, 70 miles. Am I going to make it? Who knows? And then I want to be able to share my findings in an easy to understand way because it's hard to get people excited about my gas mileage. And so I've made a few models. I got some that are likely to work. They produce continuous numeric output, so I can get any number, presumably, out of there, and then I can calculate an error metric. So the model says I have 50 miles remaining, I ran out of gas after 40, my error was 10 miles. I've got some that need modification, and those produce a discrete numeric output, so I might not get every number, I might just get, oh, you have 50 miles, or 70 miles, or 90 miles. It could be one of those. Or it produces probabilistic output, which would be, you're going to run out of gas, or you're not going to run out of gas. And error is a lot harder to calculate without driving around and running out of gas. And so, again, if I use estimated miles remaining, I'll choose a metric in this case for root mean squared error, which will just say this is how much of a buffer you have before your model might be wrong and you'll run out of gas before you thought you would. And then, again, for the probabilistic one, I can use percent accuracy. And so for the ones that are likely to work, I started with a neural net because if we're going to start big, we might as well start with the biggest. And so I used the three, like I showed with my instrument cluster, I've got those three variables available to me, my gauge level, my light, and my trip odometer. And for this particular neural net, I gave it 1,000 epochs and 10 hidden units. It was definitely overkill with less than 200 rows, but that's okay. And some pros for this particular model, it's quite accurate. It's very cool to use and very hip. And if I say, hey guys, I made a neural net to tell me how far I can go in my car, everyone's like, wow, you're so cool. And I go, thanks guys. And then cons, it's not easy to do on the fly. I don't really know what's going on, and I can't share it with you, and it's computationally expensive. And so my poor phone, it's plugged in, it's trying to run Android Auto, and this neural net, it might not happen. Alternatively, I could step back a bit, and I could use a simple decision tree, where this one, again, I fed it all three variables. It turns out this particular implementation only decides to use my gas gauge, which is handy, because it means it's less for me to think about. And I just have one tree. And it's easy to understand. It's easy to execute. I can say, hey, my gas gauge is at 1. And so I go, yes, it's less than 1.4. No, it's greater than 0.63. Yes, it's less than 1.1. I might have 113 miles remaining. Who knew? But it could be better. Distance and gauge level does imply miles per gallon. So by losing distance, we're losing some implied metrics there, because if my gauge is at, let's say, 3 out of 4, and my distance is 100 miles, I'm probably getting pretty good gas mileage. And so we're losing that miles per gallon. And then there's some memorization involved where now I either have to print it out and look at this, and that's not much better than texting, or I just have to memorize it. With random forest, if you're not aware, it's basically taking about 1,000 of these, but they're all slightly different, and then averaging them out. And so this one, I don't really know how many of those trees used which of my three main variables, but I made 1,000 of them. It's very accurate. It's not massively computationally expensive compared to, let's say, the neural net, because decision trees are relatively simple, and you're just doing a lot of them. Cons, it's not easy to do on the fly. If I'm going to struggle with one decision tree, I'm definitely going to struggle doing 1,000 of them, because that's probably going to take me a solid hour and a half, and at that point I'm dead on the road again. And it's pretty difficult to communicate because, again, I can tell you one decision tree, maybe I could give you 2. You don't want me to give you 1,000 decision trees. And then if we step over to a simple regression, a linear regression, and I'm just using gauge level, it's easy to understand, it's easy to execute, because I have this equation down here, and I say, okay, my gauge is at 1. I'm going to make this easy for myself. Then I've got 66.2 plus 55.94, and then I'm too stressed presenting to do that math in my head. But it could be a little bit better. Again, distance and gauge level implies miles per gallon, and it does require that mental math, which again, you might be too checked out on the highway to do, or maybe mental math isn't really your strong suit. But that's okay. We can make it more complicated for you. We can give you multiple linear regression. And so instead of just using gauge level, we'll add in light and distance. And it's still relatively easy to communicate, because if I show you this, and then I say, okay, just pretend there's more variables, and this line is in 4 dimensions instead of 2, you go, oh yes, of course, the 4th dimension. So simple. And it's quite accurate, but again, there's a lot more mental math, and because you're trying to think in 4 or 5 dimensions, it's not as easy to understand. And if your car, if you're bringing this home, you probably have more variables you can use at your disposal. So since I sold this car, I now have my car's own estimated miles remaining, and I could add that in, and now I've got more and more variables building it out. And so now I've got the ones that need some modification. They don't quite tell me miles remaining. They're more of a, here I'm making you do some work too. And so if I do a clustering algorithm where, again, I'm using all 3 of my variables, and I'm building out 10 centers, and so that just means I have all of my data sort of plotted out in that multi-dimensional space. I try and find the 10 closest groups I can, end up with this table of centroids. I say it's easy to execute, and that's, on the math side, watching how k-means works is actually really neat, and I do recommend it. But it's easy to execute because as long as I have this table with me, I can go, yeah, I've got like 280 miles, my light's on, and my gauge is at 0, so I probably have about 65 miles remaining. But there's lots of human factors in interpretation. It can be difficult to choose a row if you're in between. It's kind of difficult to communicate because I saw you all nodding. Ah, yes, k-means. And there's no real good measure of accuracy because at this point I only know, do I have about 47 miles or am I going to run out of gas? Over to logistic regression, things get worse. If I only use my gauge level, I have to convert and say, do I have less than 50 miles remaining? I can't get that nice how many miles. It's now, do I have 50 miles left or not? It's easy to understand. It is relatively accurate. But it's basically the same as the gauge level, because if you actually plug gauge level into this equation, when your gauge is at negative 0.25, which is the lowest it goes, then this produces, yes, you have less than 50 miles. But I already knew that because my gauge is below empty. So if we then, yeah, I did do the math a few times. I was like, what if I put it in at 0 and it comes back as, no, you have more than 50 miles. I was like, this is great. And you can see it again from the distribution of the dots. And so if we do compare the models, we'll use estimated error and estimated miles remaining. We've got our root mean square error as our y-axis. Our simple decision tree, while relatively easy to use, has some of the worst error. We get a little bit better with simple linear, then multiple linear, which is actually very close to the neural net. And then random forest blows the other models out of the water. And k-means and logistic regressions do have bars. It's not that they're failing to load. You can't measure error. It's maybe they get it right, maybe they don't, but you're never going to have a good sense until it actually happens. And so in classic Apple fashion, just like the color scheme on my slides, I'm giving you a chart with no y-axis. And I'm saying, higher is better. And so I did pass my tables around. There are numbers behind these. I passed them around to my team at Lander, and I said, all right, how do you feel about ease of use for these different models? And we agreed simple linear models are pretty easy. It gives you a y-axis, it gives you an x-axis, you do a little bit of math, and then you plot your points. Pretty simple. A decision tree, again, the problem there is it's a lot more direct from the simple linear. K-means, you just have that table. Again, you have to memorize it. Multiple, now you're doing a lot more math. Logistic regression, again, depending on where your equation is at, you might actually have to do one equation to get your odds, and then another equation to convert to probability. And at that point, again, you've missed your gas station. And then good luck using a neural net or a random forest while you're on the go. And if we look at communication, so I'm trying to tell all of you about these models. And for me, at least, telling you about simple decision trees and linear models, it's pretty easy. Same with logistic. It doesn't perform as well, but it's easy to communicate. And once you have the ideas behind simple linear, adding in multiple linear isn't too bad. Same with random forest and simple decision trees. K-means, not so bad. And then neural nets, it's easy to just hand wave and go, it works like your brain. It doesn't, but you can hand wave it for most people. And so what did I actually use to estimate my miles remaining? And this is really like the big question here. And the answer is I used my brain. To be honest, I never made any of these models until earlier this week, and I sold the car a month and a half ago. So, so I did try and really chart out. I was like, okay, what am I actually doing when I'm sitting in my car? And it's basically a decision tree, kind of. And so I would look at my gas gauge or my light or my distance, and I would get really antsy when I hit 270 miles, because I knew I had enough of a buffer to make it to Costco for cheap gas. But if I got there, I might have to turn the car off in the parking lot because I wasn't sure if I'd make it to the pump. If my light was on, I should probably get it just because that seems like the responsible thing to do as an adult. Or if my gauge is a little bit too low, then I might want to start thinking about it. And as I'm sitting here charting this out and going, okay, what nodes do I need to add? What decision points do I need to add? I realized it's basically decision tree meets k-means table. I've rotated that chart 90 degrees, but really all I did was in my head, I went, okay, I've gone like 290 miles. My light is on, and my gauge is at 0, so I should probably get gas soon. It's not so much that I'm following any one thing strictly, but as a person, I've built my own mental model of when I should get gas. And so if we think beyond the gas tank, because I said the word gas a little bit too much, and surprised I haven't gotten it confused with my own name, then we can think about maybe hospital patient readmissions. So instead of thinking, how often are people readmitted to our hospital, we can think, what is influencing those readmissions? So once we build the model and say, okay, let's say I have a very low chance of being readmitted because I'm a young, healthy adult male, but if I was an old, frail man and I went in a snowboard accident, I'd probably have a high chance of being readmitted, but that's not important to know. What is important to know is that I'm old, I'm not doing great health-wise, and those are the likely things to bring me back. And what's convenient for a hospital in that situation is they can't do anything about you being old, but they can do some other things that I've got talks on my website you can look at about it. Or if you want to go to Disney World, you can try and predict your ride wait times, but that's not really helpful because you don't care how long the wait is. You already know, they tell you how long the wait is. What you want to know is what's influencing those wait times. So if wait times get shorter during fireworks, that's a really good thing to know, and they do. Or if there's a parade, people want to go see the parade, go sneak in on your favorite ride. And again, it's not about the output of the model and telling you what the actual time will be, but finding all of the factors that influence it. And for standardized test course, a little bit of a hot button topic these days, but some people may do better just because of where they grew up, the schools they went to, the environment they had. And so saying, oh, we're going to predict SAT scores, it turns out the best predictor for SAT scores is actually zip code. And so it's not how much time they spent studying, it's not the schools they went to, but kind of is because a lot of the times people go to neighborhood schools. And so if we try and think about it as a whole, accuracy is great. Like Jared yesterday, wherever he went, more complex models can produce fantastic results, but they can also be a lot more wasteful for marginal gains, and sometimes they're actually a little bit worse. And so accuracy is good, but so is explainability and executability. And sometimes it's okay to sacrifice a little bit of that accuracy so that you can communicate it to the people around you so that all of you have a better idea of what's going on. And that, my friends, is machine learning for people.